I'm reading a book about anti-gravity. It's impossible to put down. Okay. How many ears does Captain Kirk have? 3. A left ear, a right ear, and a final frontier. Okay, I'll stop.
Okay, welcome everyone to Astronomy on Tap number 44. We see a lot of new faces and a lot of old faces, as in like regulars. Everyone's looking young and proud. And yeah, this is really exciting. We're doing kind of like a special edition because it is February, and February is Black History Month. So we're gonna have a lot of special, cool things happening tonight. So get ready.
All right, so first things first, announcements. Please like and subscribe to us on YouTube. We have a YouTube channel where we're also airing the show live right now, and in times where we need to go online for various reasons, that's where we'll be. And you can also follow us on these other social medias, so AoT_BCS on Instagram and Twitter, or just AoT BCS on Facebook. And you can also find out more about Astronomy on Tap and the events at this website link. And if you would like to help support the Grand Stafford, which you should because it's the great place that you're at and that allows us to host this, you can send them a tip on Venmo at Jose Quintana 20. So put Stafford tip in the description. That's what it's for. So please tip your bartenders tonight. It's really great that they let us do this every month. And you can also donate to us on Venmo or Cash App at AoT BCS. And if you donate $15, you get a free t-shirt or a free mug. And if you donate $2, then you get a free sticker. Free stuff. Or other things. Oh yeah, we have a lot of free stuff over there. Not all of it's free, but a lot of it is. And these are new mugs, and I think Sylvie designed them, so you wanna...
I mean, I can design our logo, which is the cool person there with the beer, the space beer. But yeah, these are super new, so limited edition for now, unless we make enough money to get more. But yeah, and then they have our little Astronomy on Tap in the back, Bryan College Station. And then obviously our social media tag, which is AoT_BCS, Instagram, Twitter, and Facebook. Maybe TikTok someday, I don't know. Yeah. No, maybe not. That's a lot of work. Well, I guess I'll say this. Our next event is March 23rd, 1 month from now, and it's also the 4th Wednesday of every single month, unless stated otherwise. But we've never actually had to cancel a show, only for COVID reasons. But yeah, the 4th Wednesday, March 23rd, come through. And then lastly, talk to the local astronomers. We are wearing glow stickies and ask us questions about space and the universe and stuff. Okay, so our first talk of the night
is going to be given to us by Thomas Onyango. Thomas is a graduate student at Texas A&M studying nuclear physics. And there's certainly a lot of fun facts about him, but I just don't know any of them personally. So Thomas, would you like to give a fun fact about yourself?
You know, the only thing that comes to mind was at a music festival in Croatia. It was a good time.
Okay, everybody give it up for Thomas. Yeah.
I'll be talking to you guys about neutron stars.
Yeah.
As you can see from the first slide, oh, it's not spinning. Oh, you didn't have the little animation going. That's a shame.
Oh no.
The O in neutron, it spins around because it's a pulsar. But maybe next time. Okay, so neutron stars are a star, but how do we get stars in general? And so what happens is that after the Big Bang and after inflation and during expansion, the universe contains a lot of hydrogen and helium gas. That gas is neutral, and so the only way it interacts with itself is via gravity. And so what happens is that it clumps up and it clumps, and depending on how much of the gas clumps together, coalesces, you can get many of the astronomical things that you've heard of. You can get massive stars, low mass stars. All right.
It should be on.
Yes.
And then there's also a laser pointer.
Trying to figure out which button is the. Oh. Yeah. It's upside down. You asked me to think about the pointer, yeah, I'd be all on top of it. You get your massive stars, your low mass stars, even brown dwarfs. Maybe that can be another presentation. I don't know what those are. But what we're talking about are neutron stars. So you need a lot of mass in your star. And then what happens? So you get coalescence of astronomical gas that coalesces into a massive star, more than 8 times the mass of our sun. And then what happens is that the way a star maintains its structure is that gravity pulls it inward and brings it together, but then that causes nuclear reactions to go on inside. And so those nuclear reactions put pressure outward, and so they form an equilibrium, and the star has a more or less constant size. But as that nuclear reaction fuel is depleted, you get a red supergiant. And then that red supergiant, it'll core collapse into a type 2 supernova. Most of the material is ejected out violently, as one of the papers said. I don't know why it was violent. I guess they're no gradual ejection. Gentle ones. And then what's left is the core. Depending on how big the core is, if it's too big, you get a black hole and X-ray emissions and also a quasar. But if it's small enough, then you get a neutron star. Stars spin back into stage. And after the supernova happens, a lot of the material is ejected. But if the core is left and it's still spinning fast enough, then that spinning neutron star generates a magnetic field. And neutron stars typically are left with a lot of angular momentum. They're spinning really fast. So they have really strong magnetic fields, and this causes their material to be ejected out along their magnetic poles. Those ejections, not the supernova ones, but the neutron star ones, those happen, we can see those because they're bright flashes of light. They pulse because every time it spins, we can see it at least once per revolution. Maybe we should just name them after the pulses and call them pulsars. Oh, don't worry. During this presentation, you'll see how clever scientists can be when naming things. So neutron stars, what are they? They're named as such because neutrons are the preferred component. If you go down deep enough, like inside the crust, They're the core of a dead imploded supermassive star. And the current belief is that neutron star mergers, which are just two neutron stars colliding together, are the explanation for super heavy elements, elements heavier than iron, based on more theoretical calculations, but it's been whittled down as opposed to just, I forget what the previous explanation was. It was related to neutron stars, but now they said you need two of them. They're one of the brightest objects in the universe, debatably. They're the brightest intrinsically bright. There we go. And because of their really fast rotation and density, they can produce some of the strongest magnetic fields in our universe. But what's really unique about neutron stars is that they're really compact. They have a 15-mile diameter, but they weigh as much as like 1 to 2 times our sun. So I have this slide of the neutron star composition. You don't need to know all the details. You just need to know that there's an atmosphere, and then we're going to go to the outer crust, and the inner crust, and the outer core, and then in the inner core. The atmosphere is not all that interesting. Those are some of the remaining elements from the core collapse of the supernova. It's where most of the light stuff is found. You've got your hydrogen and carbon, so that's all that's, yeah. You got 6 elements. Try building a world with that. And it's really thin. It's only 4 inches thick. The outer.
10 inches?
Yeah, 10 centimeters. It's dense. You saw the first slide, remember? It's thick. So now we get to see some wacky stuff happen. Right before the supernova, as the star was dying, it was producing heavy elements around the size of iron. And this is where, after the core collapse, this is where those elements reside on the outer crust, where they stay. They don't go any further. They're too heavy to stay in the atmosphere. But then, as you'll see, their composition isn't right to be found deeper within the neutron star. And so what we have here, before on a larger scale, we had a balance between gravity and nuclear fusion with pressure. Now we have a balance between gravity and the electric propulsion. Atoms have negative electrons, and the cores are positive protons and neutrons. So you've got that electric propulsion, and that balance creates a lattice, which just means that your nuclei are organized in a nice, neat little pattern like this, similar to this. Let's go deeper. Let's penetrate even further. And now we're in the inner crust, and it's at this level that our protons and electrons learn to become very close friends. We're at the periphery of the inner crust. It's being held up by, I don't know if you guys remember the Pellet exclusion principle from high school chemistry. If not, that's fine. The Pellet exclusion principle just means that 2 electrons can't occupy the same space. Now you can impress your friends with that at parties. If you want to make it seem like you're in the biz, you can call it Pauli blocking because those states are blocked. So as we go deeper within the inner crust, the repulsion, that pressure from the Pellet exclusion principle, it's not enough. And this principle can never be violated. So what the constituents do, protons absorb the electrons and form into neutrons and neutrinos, but we don't even know what neutrinos are. And so that's why it's called a neutron star. That's the preferred state when you're deep in there. In order to make sure the electrons don't occupy the same space, you just form more neutrons. But as you go deeper and deeper in, your nuclei, they become too neutron rich. There are too many neutrons in there. And so your nuclei, which are your protons and neutrons, they'll start to drip neutrons. The individual neutrons will drip down further, while the nuclei, the still pretty stable nuclei stay at that level. So now we get to the slide. This was the main motivation for me wanting to look into neutron stars. It's these structures called nuclear Impasto. This is where physics naming really shines. We've got all sorts of things. There's gravitational spaghettification. We've named the particle accelerator Rick, but I think this is the best. I think it's the best. So you've got your protons and neutrons. You've got your lighter nuclei in this level. We're at the outer core, and what happens is that the pressure and the density is so intense that they're being forced to touch. The nuclei, they touch just like this, they bottleneck, and they form gnocchi. And that's fine, but as we go deeper and further, the gnocchi start to like form into long strands. They're not like perfectly cylindrical, they've got some deformations, but they form into long strands called spaghetti. And then your spaghetti, it's not perfectly straight, but as you go deeper and deeper, you get more compression, more density, more pressure. And so the strands of spaghetti start to touch and form into sheets called waffles. And the waffles, they have holes in them because of the deformations in the spaghetti. But as we go deeper, with more compression, we're still in the sheet, we're still got sheets, you get lasagna. So no more holes in your waffles. Yeah, according to new physics, lasagna is just a waffle without holes, I guess. We go deeper, more compression, more density, more pressure. The deformations in the sheets of lasagna, they start to touch, and you get I guess it's just called defects. This didn't look like any food, so they just called it defects.
Funnel cake.
Yeah, you might be onto something. Anyone here studies neutron stars or supernova, you could just like put the word out there in the scientific community. You could call this intermediate stage between lasagna and anti-spaghetti. You can call that funnel cake. It's not pasta, but neither is waffles, so I think it's okay. So you've got your defects, and now your defects are really either they're forming holes of their own. So now instead of like gaps between the sheets, you've got more like cylindrical holes in your sheets, and you get when those holes are in the shape of the spaghetti. So now you've got anti-spaghetti. That's when your spaghetti tastes bad, I guess. More pressure, more density, more compression. And so now the holes are being cut off and the holes are deforming, I guess. And so now you have anti-gnocchi with the holes of what would be shaped as gnocchi. And that's the pinnacle of science. This is cutting edge stuff. This is what we believe is going on in the outer core of neutron stars. And now we get to the inner core where the real mysteries lie, where it's anyone's guess. At this stage, there's more pressure, there's more density, and we're really not sure what goes on here. There might be more protons and neutrons. If so, the neutrons are neutral and they get compressed into a superfluid. The protons have a charge and get compressed into a superconductor. It might be that this isn't stable enough. There might be too many violations of the Pellet exclusion principle. And so some of them might get reformed into hyperons. Those are like your regular nucleons, but they're heavier. They also contain one or more strange quarks. You might just get straight up quark matter, which means you get that if your protons and neutrons, they melt just from too many violations of Pellet exclusion principle, and it gets too hot there. But what even is a quark? That's a strange word. Why would I say that? So now we'll do a nice gentle refresher through the states of matter you've heard of and you haven't heard of. You've got your solids, and then we increase temperature, you've got your liquids, then we increase temperature, you've got your gas, then we increase the temperature into something a little more interesting. Also try and remember this diagram of an atom. You'll see it again later. Electromagnetic plasma, or any of these plasmas, have to do with the free-flowing charges. Your gases are electrically neutral, but once you give your electrons enough temperature, enough thermal energy to escape their atom, you get electromagnetic plasma, and that's fine. You've still got positive nuclei doing their thing, and your electrons are whizzing around. But once you start heating that up even further, your protons and neutrons, they no longer have to hug each other. They're no longer married. They're doing their own thing. And so now your electrons are freely roaming around, but so are your protons and neutrons. You heat up your substance even more, your protons and neutrons, they can't handle the heat. So they melt right there, Wakey Witch to the west, into their constituents, into quarks. Electrons they're still fine as far as, they don't melt in there. And so this is like the periodic table, but for particle physicists. And so protons and neutrons are made up of up and down quarks. And then I also circled strange quarks. That's the technical name for it. It's not a modifier or a characteristic. We've got up, down, charm, strange, top, and bottom. And this used to be called truth and beauty, but that's where we drew the line in the naming convention. We couldn't be too whimsical with the names of these things. And so back to that slide about quark matter, the protons and neutrons might break down into up and down quarks and potentially even strange quarks in order to avoid violating the Pauli exclusion principle. And what's crazy is that this substance, this quark matter, is very stable. It's composed of up, down, and strange. And according to my research, my light research, this material is actually a little infectious. Because of its stability, if it were to interact with your normal atoms and stuff, it would convert them also into strange quark matter. And based on what I was looking into was that it had a very interesting sort of like doomsday scenario. If you got your neutron star merger, two of them colliding, and they eject their contents out into the universe. And all it would take was just a little bit of strange quark matter called a strangelet. And if it just like hits your asteroid, it hits your binary, it hits your asteroid, your star, your whatever, your planet, it would just slowly but surely convert the entire material into strange quark matter. Scary stuff. Nope. There's no sound. Thank you. Thank you for your time. Any questions? I see two hands up from the same person. Yeah. Oh, easy ones, right?
Yeah.
Okay.
Okay, so first question. If you had to choose one of the nuclear processes to take the sample of, assuming you could like lift it up.
Right, yeah.
Which one would you use? Can you repeat the question?
So she asked me if one of the nuclear pasta phases, if I had to pick one, assuming I could lift it, because remember, it's about the weight of the sun, but also the density of a diameter of 15 miles. You go back to that. So, bingo. It would probably, it's funny, I've also been thinking about this. I think it would be the lasagna. There's something, for some reason, I feel like it's easy to handle when it's drawn like this, where it's just like sheets easily separated. The other one, or maybe waffle. Like you can just put your finger, you can bowling ball it and then just eat it like that.
So what do you think of the taste like?
Ooh, probably a little hotter than a pizza roll, but not too crunchy, I think. Not too crunchy. Yeah, it's textured, but not too crunchy. There's already, I don't think it'd be too soupy. That would be more of, probably this layer is pretty soupy, but then it starts to get a little too rigid. It might be like peanut butter, peanut brittle. You, sir.
Yeah, so, thank you, Tommy, graduate student.
Where at?
St. University, it's down the road.
Small world.
So what's the length scale on these diagrams? Like how big is this spaghetti? How long is this spaghetti?
Oh, how long is this spaghetti?
Yeah, how long and how thick
The thickness is on the order of small nuclei, so less than 10 Fermi over less than 10 femtometers, a few Fermi. As for the length of the spaghetti, I don't know of any upper limits. I mean, you wouldn't ask the dimensions of a lattice, would you?
Yeah.
You might, yeah. Infinity? Yeah, that's the length. Yes.
So if you put one of the phases of nuclear pasta in a waffle iron, would you get a new phase of nuclear pasta or just waffles?
You see, I went straight to waffles and then I was like, well, nothing happens. It's already a waffle shape. But you probably mean the other phases, right?
Yes.
Assuming your waffle iron was made up of also neutron star material so you can move things around. Yeah, I'm gonna say yeah. Yeah, you can convert them into other phases, assuming it doesn't violate the Pellet exclusion principle.
It would have to be like born from the core of the neutron stars, right? To be able to warp.
You just,
stuff.
It probably comes with like 2 plugs, so that way you can draw twice as much power.
Right.
Yeah, little man, what's your question?
My question is, what are neutron and the strange number of stars?
Neutrons are just a component of an atom. They're a part of. What are quarks?
Yeah.
Okay.
I don't know proton too.
Okay.
I don't know neutron.
You recognize this symbol of, or like this diagram of an atom? So right here are where your neutrons are, these ones. So you've got your electrons, they whiz around pretty far from the core, the nucleus. And then that nucleus is made up of protons, which have a positive charge like a battery. And then these neutrons, they're not charged at all. They're like the protons, they weigh almost as much, but they're neutrally charged. So like if there was no battery. Those protons and neutrons, they have their own building blocks, and those building blocks are quarks. And these six elements of our physicist periodic table are the quarks. They're just building blocks for your protons and neutrons.
Okay, we're out of time. Thank you, Thomas. Fun fact, it is his first time at AoT. Okay, so we're not doing trivia just yet. So sorry for my trivia crew that I see you guys are ready. You can start handing out the stuff though. So we're gonna do trivia after this really awesome segment called Who's Up? Usually we do a segment called What's Up, where you learn about what to look out for in the sky. But this month we wanted to do something special for Black History Month. So we're gonna do Who's Up? Who can you look for in the internet web? And then also just quickly, don't forget to tip your bartenders. They are amazing and important. And this is Yaswant, graduate student in astronomy, part of the supernovae group. The supernovae group is like right there if you guys want to go ask some questions about supernovae. And Yaswant has a really cute dog named Lulu. And yeah, there's a lot of other fun stuff about Yaswant, and I always forget what to say too. But give it up for Yaswant.
All right, welcome to Who's Up? So normally I do What's Up. But that's what we're going to do. Who's up? So I'm going to highlight some really cool people doing some really, really important work. So the rising stars, you could say, in astronomy. And so the first one, just going a lot of tangents to this talk. Okay, so first I want to talk about quick shout out to Black and Astro. This is a super awesome group that are doing a lot of work to highlight these people and the awesome work they're doing. And so I could not have done this without the awesome work that they've done. You can check out Black and Astro. There's also Black and STEM, Black and Physics, a lot of other communities. They're doing really awesome things. They have their own website called blackandastro.com, and also the website Astrobytes, which takes astronomical papers and condenses them down to really approachable ways. They do a profile series based on Black astronomers and Black and Astro. It's also super awesome. So a quick shout out to them to thank them for all the work they do. I also want to talk briefly about the history of Black and Astro and where it came out of. So to talk about that, we first have to talk about this incident back in 2020. Some of you may remember this from the news. In Central Park, there's this black bird watcher named Christian Cooper who's just out in the park watching birds. And then a white woman named Amy Cooper was walking her unleashed dog around the park. Dogs are supposed to be leashed in the park. Christian Cooper was like, hey, can you please leash your dog as they're supposed to be? And Amy Cooper was like, hey, police, this African American man just threatened me. Come get him. And so this is all captured on video to prove that she was lying. He never threatened her. This also happened on the exact same day as the arrest and murder of George Floyd. So that was like a double whammy for that day. In response to this, Black bird watchers, field biologists, ornithologists, and so on and so forth, they organized this thing called Black Birders Week. This is sort of the first in the series. In response to this incident, they wanted to highlight the unique challenges and difficulties that are faced by Black folk who go out in the field and do all this kind of really important work. And other movements started to follow suit for other fields of study works, and that's sort of where Black and Astro came from. And so Black and Astro is doing a lot of great work highlighting a lot of the awesome Black astronomers on the field, talking about not just the struggle in the field, but also highlighting the awesome science they do, because it's really important to highlight both of those things. The first person I want to highlight for who's up is Ashley Walker, who's the founder of Black and Astro, co-founded Black and Chem and Black and Physics. Because of this work that she did, the academic journal Science recognized these campaigns as part of their breakthrough prizes in the year 2020. So that's pretty awesome. She recently graduated from Chicago State University as the first astrochemist in the university's history. And is currently a PhD student from Howard University, researching the atmosphere of exoplanets and solar system objects. Her current work is really interesting. She's looking at various elements that are abundant and there's most abundant in this atmosphere of Titan, which is one of Saturn's moons, and using that to try to see, okay, here's what we see in the solar system, how does it compare to what we see out in exoplanets? You can follow her on Twitter at that astrochick. Next one's by Caprice Phillips, who I actually personally know, kind of. I don't know if she remembers me, but I know her. She's a current lead organizer of Black and Astro. She's a PhD student at Ohio State University, but she did her master's at UT Austin, which is where I met her when I was an undergrad. She's currently working on detecting biosignatures on gas dwarfs with JGST, which just launched. And some beautiful images that have come out soon, so keep an eye on some fun stuff for that. For those of you who don't know, gas dwarfs are exoplanets that are between the size of Earth and Neptune that are mostly gaseous. And these are really useful for trying to find signatures, their atmospheres for various things, such as ammonia, which is which is what's considered a biosignature. It's not easy to make naturally. The best way to make ammonia would be to make through some sort of biological process. So if you see an ammonia in an atmosphere, that'll suggest there might be some sort of biological background on the planet. And her paper in December showed that by simulating JWST observations, you should be able to detect ammonia through these atmospheres. So that'll be really exciting. That'll be a great thing to go look for. She's also a McNair Scholar. This is a U.S. Department of Education program that's tries to help students from underrepresented backgrounds get ready for graduate and doctoral programs. She's talked a lot about this, and she's talked about how she grew up in a small town in Arkansas, went to a really small college, never really, wasn't really sure if going into academia or being an astronomer is for her. But programs like this were really instrumental in helping get to where she is now. So I just want to highlight the great work they do. Also wanted to go on another tangent and talk about Dr. Ronald McNair. I highlighted him last year in my profile of Black astronauts. He's just super awesome. He's a laser physicist. He's a presidential fellow, Ford's fellow, a bunch of different things. He's a 6th degree black belt, accomplished saxophonist. He earned 4 honorary doctorates. He did all of that before becoming an astronaut. And he's the 2nd African American astronaut, so he was really cool. And you can follow Caprice and learn more about the stuff she's doing with Caprice Phillips on Twitter. The next person I want to talk about is Naya Butler-Craig, who's the co-organizer of Black and Astro. She's currently a PhD student at Aerospace Engineering from Georgia Tech, working in the High Energy Electric Propulsion Lab, which I don't know anything about, but it sounds really cool. She makes really cool rocket videos and stuff, so that's cool. But she's also Forbes 30 under 30 honoree, so you know, I only got about 4 years left to make it onto that list. So you can follow her on Twitter, Astronomical. She really recently started a vlog on her YouTube channel, so you should check that as well. Particularly if you know any young kids who might be interested in learning what the life of a PhD student is, that might be a good place to go check it out. The next person I want to talk about, another person that I actually know, and this person actually follows me on Twitter, so that's a flex. This is Dr. Sinclair Manning, who's the first Black person to graduate with a PhD in astronomy from UT Austin back in 2021. Currently a NASA Hubble Fellow at US Amherst. She studies dusty star-forming galaxies in the early universe. She put a paper out back in November. She found 2 high redshift galaxies that were observable on the radio, but because they had so much dust, they're completely invisible in the optical and in the infrared. So you can only see them in the radio. And she did a bunch of studies on this and found out that they were forming hundreds and hundreds of stars a year. One was forming about between 1 and 200 stars a year. The other was forming about 800 stars a year. And the fact that we just can't see any of that is completely obscured by dust. It's pretty interesting because in theory they should be spitting out just tons and tons of really, really bright light. She also knows way more about soccer than most people do. She's a great follow if you like following the US Women's National Team or watch the Premier League. She live tweets like every single game. So I highly recommend you give her a follow at SMany206. Next up, we have Dr. Carl Fields. He's super cool. He's the RPF Distinguished Postdoctoral Fellow at Los Alamos National Labs. He's a computational astrophysicist who makes simulations specifically on stellar explosions. In December, he made this paper talking about the collapse of rapidly rotating massive stars. And if you follow him on Twitter at Carl.Sagan, he has some really, really great, he posts really, really great GIFs and stuff of these explosions. There's really, really marvelous. And they're full 3D and everything. Unfortunately, I couldn't get them to load on Google Slides for some reason, so I couldn't show it to you. But you know what? That's just easier for you to go to the Twitter and follow him. He's also a Forbes 30 under 30 honoree in their science division. So we only got 4 years left, huh? Okay. Plenty of time. The last person I want to talk about is Dr. Moya McDeer. Fun fact, she grew up in a log cabin, like a Lincoln-type log cabin over in Pennsylvania, went to Harvard, studied both astrophysics and folklore and mythology, and then got her PhD in astrophysics from Columbia. She studies the galactic habitable zone. So there's the idea that for exoplanets to be habitable, they have to be in the specific zone. If they're too close to a star, they'll be too hot. If they're too far away from the star, they'll be too cold. If they're right in the middle, it's great, but there's all sorts of other effects like radiation and asteroids and all that stuff. And she studies the galactic habitable zone. So the idea that where these stars actually form and move in the galaxy itself can affect the probability that they can create habitable planets and stuff like that. So she studies that sort of thing. She wrote a book called The Line Hordes. This is based on her senior thesis that she wrote for her folklore and mythology class. That thesis is a sci-fi novel, and the novel itself is a sci-fi novel that's set on an exoplanet that she studied for her astrophysics degree. You can check it out for free on her website, by the way, so it's super cool. She's the host of the Explore podcast. So she explores with guests every week how authors in movies and books and novels create fictional worlds and how they use these fictional worlds and what that can tell us about various topics, which is super useful if you're like a budding author and you're trying to figure out how do I make my fictional world more, good. I play D&D, and so this is like a great resource for me. And so just like a teaching god. She also hosts Fate and Fable, which is a YouTube series on the PBS Story YouTube channel. It's a great show. I think they just dropped a new episode. There's an episode the other week about humans' fascination with cats, which is really interesting, and like how it goes all the way back to ancient Egypt. But yeah, her show explores influential myths, mythological stories, and how they shaped humanity. So they all make me feel really bad about what I'm doing. Anyway, that is Who's Up.
Any questions? All right. Okay, we are now going to commence the trivia. Black History Month themed. Oh yeah, sorry, does anyone need paper? Like the trivia paper specifically, not just blank paper. If you don't have the trivia paper and you would like to participate in trivia where you can get prizes if you win, raise your hand and one of the astronomers will make sure you have everything you need. But it seems like everyone's ready to go, so let's get started. Okay. What astronomical phenomena did Benjamin Banneker write about in his Almanac? Was it A, neutron star mergers, B, supernovae, C, solar and lunar eclipses, or D, variable stars? Tough one. Okay, next. Question 2. Who is the author of the book Hidden Figures? Is it A, Margot Lee Shetterfly, B, Katherine Johnson, C, Dorothy Vaughan, or D, Mary Jackson? Question 3. In what year did Harvey Washington Banks become the first Black person to earn a PhD in astronomy? Is it A, 1876, B, 1961, C, 1919, or D, 1981? Question 4. Who was the first African American in space? Is it A, I think that's Guyon Bluford, B, Mae Jemison, C, Bernard Harris Jr., or D, Robert Kirby? Okay, question 5. Where did Barbara Williams in her PhD? I think that means oh. Okay, where did Barbara Williams earn her PhD? Is it A, UC Berkeley, B, Texas A&M, Giggle, C, Stanford, or D, University of Maryland?
Question 6. How many PhDs have been given to Black women in physics and astronomy? Is it A, 1,015, B, 578, C, 50, or D, 187?
The US.
That's a good question. In the US or in the world? I'm assuming in the US. In the US. Question 7. Gregory Robinson is the program director for which space telescope? A, JWST, B, Shields, C, Hubble, or D, Gaia? Question 8. Who is the most published Black astronomer? Is it A, Barbara Williams, B, Gabriel Barcy, C, Aaron Evans, or D, Ronald Mallet? Question 9. Whose memoir is titled Time Traveler, a scientist's personal mission to make time travel a reality? Is it A, Gabriel Barcy, B, Stephen Hawking, C, Ronald Mallet, Or D, Arthur B.C. Walker? Last question. Who has had a sack in the Super Bowl and has also been to space? A, Reggie White. B, Julius Peppers. C, Michael Strahan. D, Chris Dolman. Strong? Okay. Strand? Are there any questions that need repetition or that you would like to go back to? Everyone got it?
Yeah, can I have the answer for number 8?
Yes, after the break. We'll go over the answers after this quick break that we're going to take right now. So chit chat, talk to astronomers, follow us on Twitter and Instagram, and tip your bartenders and get some drinks and have fun. Woohoo! Jesus, music. And we're gonna go over the trivia at the end, not after this. I know.
And I'll be like, well, this road out simplification. 1/2 minus So in the hour, you got the waves.
Some neutron stars get organized, but as they're spinning, they lose energy because of the drag in space. And so
Really smart right now. I mean, it's like a white hole, so the yeah, it's on. That's good. People like channel that kind of Like legal audio. That's why like that sky is running in the sky. Yeah. So there was some for a while. That's too much. And then it's not for all right, this is enough. I knew where you were
All right. I love the enthusiasm and the chatter. We are ready for our next segment, In the News, Astronomy in the News. just a reminder, we will be going over the trivia answers at the end. So there will be a winner. And then, yeah, and then there's another speaker coming soon. But before that, we're gonna see what's happening in the news this month with Alex Riley. Woo, give it up for Alex.
Hey everybody. So first things first, my name is Alex Riley. And the second thing you need to know is that I'm a lightweight and I'm 3 drinks in tonight. So this is going to be great. All right, so let's get to the news. We're going to talk about what happened in the news science-wise this past month. So it's very cool. First thing, the Hubble Space Telescope effectively, I'm okay with calling this effectively, found a lonely floating black hole out in space. So the method that was used for this was something called gravitational lensing. So the idea here is if you're staring off into space and you're staring at a particular star, and some kind of massive object passes between you and the star, and everything's lined up just right, you can get, because of weird like Einstein general relativity stuff, you can get kind of multiple images popping up and a magnification of the total brightness of the star. And so you can see this like in these images. So basically there was this star, and if we took a picture of it in August 2011, it's very, very bright, and it starts dimming over the course of several years, and this is what it looks like normally. And you can see this in this image here also. Over the course of time, there's this really big spike peaking where this is like thousands of times brighter than the star normally is. And the reason for that is because something is passing in front of the star temporarily and then moving off. And so because of the way that of how much of this brightness happens, this gives you a time, basically how fast the intermediate thing is moving. And then if using the Hubble Space Telescope, they also looked at basically how much this star moved relative to when there isn't something passing in front of it. And so that movement of the images across the sky during the event, if you combine all those things together, including with this magnification spike, you can measure a mass of the thing that passed in front of it. And that thing that passed in front of it did not emit any light and was the mass of several stellar masses, several times the mass of the sun. And so we think it's a black hole, basically. And this would be the first isolated stellar mass black hole that's ever been detected, period, end of story. Pretty cool. Yeah. Okay, so second story, a new, at least to us, planet in our kind of immediate neighborhood. So Proxima Centauri is a really small star, a red dwarf, that orbits Alpha Centauri, which is actually itself like a binary star. So you have 2 stars orbiting each other. A third star orbiting those 2, that's the star that we're going to be focusing on here. So Proxima has already had 2 planets associated with it. I just supposed to fix this. I forgot to fix this. So this should say B, and then this should say C, or all together now. B, C. Great. All right. So, sorry?
Are the 3 stars all on the same plane?
I don't know. So the question was, are the orbits of the stars all aligned? The answer, I don't know. We're gonna move on. So a planet, so that we named Proxima Centauri. A is the star, so B is then the big planet that we detected. And then C, because it's the second planet we detected from the star. So we've already known essentially about two planets around the star, which, by the way, I think I said this, is the nearest star to our sun, like, period, end of story. Now we have a third. And so if this is B and this is C, we call the third planet
D.
Great. Y'all are astronomers. That's good. Right. So we detected this planet with a really cool method called the radial velocity method. And so the idea here is it's sort of been this is what this GIF has been going nuts over this entire time. As a planet is orbiting the star, it kind of tugs the star in a particular direction. And so if we're an observer over here, and we're measuring how fast the star is moving relative to us, it'll kind of wiggle, right? And if we can detect those wiggles, then we can associate, oh, the star is wiggling around in a way that looks just like if there's a planet orbiting and wiggling it around. And so there's a planet there. But this wiggle is so small and not very fast. This is 39 centimeters per second, which is basically like less than walking speed, right? Like a normal human walking speed. That's the level of precision that we're calibrating here for these very far away stars, right? But if you map that out, we know the mass of Proxima Centauri, more or less. And so it works out to be around a quarter of an Earth mass with about a 5-day period. So every 5 days, this planet is going around its star once, which is ridiculous. That means that it's probably very warm and all these other things. But yeah, so we have a new planet. It's right in our neighborhood. Very exciting. We know more about these things. Third and last kind of big story. Our sun burped, basically, really loudly. This kind of tones it down a little bit. This would be really, really bad. It would be very scary if this happened here. So the year was 7,176 BCE, like give or take 9,800 years ago, something like that. There was this massive 1 in 10,000 year solar storm. Okay. And so when a solar storm happens, you can kind of have this massive what's called a coronal mass ejection. Basically, the star shoots out a whole bunch of material from its magnetic field. It goes further than the magnetic field needs to take it, and it just bursts into a massive outpouring of star goop and particles and whatever else have you. And that eventually hits Earth. Now Earth has a really awesome magnetosphere that kind of shields us from a lot of what the sun puts out. But eventually that goop, those cosmic rays, can scatter off the sky. So an example of this is you'll have maybe like protons hitting nitrogen or oxygen and creating beryllium-10, which is a radioactive thing. And now all the biologists in the room are like, oh, if it's radioactive, then that means that we can use it to age things. And you're right. So what scientists have done, they've looked at these very large ice sheets in Greenland and Antarctica and found very large spikes of the beryllium-10 and all these other things that date back to, that's where you get this very precise 7176 BCE number. Because once it's radioactive, we know a whole ton about it and how it ages and all that stuff. And so you can very easily back out a pretty precise number. Now the spooky bit is that this happened right at solar minimum. So let me explain that a little bit. So the solar activity of the sun, we got, yeah. Actually is like pretty periodic. It dips and increases and spikes and falls back down. And this happens on basically an 11-year time scale. It's very precise, roughly one 11 years is how it takes to go through this period. Now, up here, there's a whole bunch of solar activity. You have a lot of these kind of coronal mass ejection things, solar winds, all this other stuff. That's when this is very active. When it's at a minimum, this doesn't happen very often. Everything's very calm, so on and so forth. Now, 716 BCE, if you just rewind the clock a lot, divide by 11, is actually around when these minima would occur. And that's not great. That means that we can still have these really massive solar winds, these massive solar storms, but at a solar minimum, which is kind of counterintuitive. And this would be really bad if it's happened like present day, right? So if you had one of these really big, massive ejection events, okay, I forgot to mention this. This is like a real picture, like real data. This is not an artist at all, which I think is awesome. So if you had one of these events and it happened to be pointed at us, hit us, we get showered with a whole bunch of sun goop, that'd be really bad. You have lots of particles that would hit our atmosphere and shower down on us. One really fun thing is that it creates a whole bunch of extra electrical signals that get caught up into our power lines. So you would effectively just like blow out the entire electrical grid of every country at the same time. That wouldn't be good. And so we kind of like, as scientists working with like policy people, we need to understand how these things happen and how to make it so that if one of these events does occur, that we wouldn't be screwed for a little bit, basically. I like to end these things on kind of a fun look at this picture. So this is just like two interacting galaxies, one of which has a whole bunch of gas and even sucked out the gas from this other galaxy. And because they're interacting, this triggered a whole bunch of really cool stars. So that's why these things are very blue. You have a lot of really blue stars here. That tends to show a lot of ejections. And then I also forgot while I was building these slides, but we mentioned JWST, the recent space telescope that was launched. That has been kind of calibrating its mirrors and getting everything kind of aligned now that it's out at L2 where it's going to be living. JWST actually took a selfie of its mirror alignment process, and so this is the actual image from the telescope, and it's taking a selfie. I didn't know it could do that, and that's super cool. So that's what happened in the news. Do we have questions? No. Good. Cool.
Okay, thank you, Lexi. All right, so next up we have Jacqueline Antwi-Danso. Jacqueline is an astronomy graduate student at Texas A&M. Her specialty is extragalactic astronomy. Fun facts about Jacqueline: she grew up in Ghana. She loves to dance. She gives great hugs.
Thank you very much, Abby. So let me just start by saying that when I picked this title, for some reason, I was thinking about Pokemon. And then as I was preparing my talk, I realized that I didn't have enough time to go through all my Pokemon jokes. So I just want to start by apologizing for no Pokemon jokes whatsoever. But I have other jokes, so hopefully those will suffice. Okay, so this is an extremely red galaxy that was formed when the universe was less than 6% of its age. It was actually found by a former Texas A&M grad student, Ben Forrest. And yeah, then some of you remember him. And it's actually a really, really weird galaxy. It's really massive. So it has a stellar mass that is about 100 billion suns. So 3 times the mass of our galaxy, the Milky Way. And in addition to this extreme mass, we found that it has other really extreme properties. So at its peak period of star formation, it was forming stars at a rate of over 1,000 solar masses per year. And just for comparison, that galaxy that Lexi showed that was forming stars, those types of galaxies form at, let's say, a rate of 100 solar masses per year. And this is forming, or this was forming at its peak period, thousands of solar masses per year. And that happened all within a very short period of time. And then after that extreme period of star formation, it quenched very rapidly and then just evolved passively. And so because of these really weird and extreme properties, some have dubbed these galaxies, monster galaxies, because again, they're weird. And in addition to these very strange properties, we can't reproduce them in our best state-of-the-art cosmological simulations. They're just not there. So what exactly is going on here? There seems to be some disconnect between our understanding of how galaxies actually grow and evolve and what reality says. So that's what this talk is about. I'll spend some time going over the background and why we think this is actually a big problem, and then why we think the solution is actually finding more of these galaxies, studying their properties, and then tying them back to theory. I'll also spend some time going over the progress that we've made so far and any outstanding issues that we think James Webb will answer in the near future. So why exactly do we need to understand how structures formed in the early universe? And this is actually one of the big goals of astronomy, to form a self-consistent framework of how structures evolve from the very, very early beginning, from the Big Bang all the way up to the present day. And so this is our current cosmological framework for how this works. We think that the universe is made of three major components. And the dominant component is something that we don't know that much about. And in true astronomer naming fashion, we call it dark energy. And so all we really know about this is it's responsible for the accelerating expansion of the universe. The other major component is something that we understand slightly more about, but not quite yet. So we call it dark matter, because it behaves kind of like matter. And then the remaining 5% is what we are actually familiar with, so ordinary matter. And this model has actually been really successful in in explaining a lot of the observations that we've seen so far. So from things like the large-scale structure of the universe, to the initial conditions of the Big Bang, to the elemental abundances during the Big Bang and the accelerated expansion of the universe, and so much more. So it's a really successful model. There's a saying in statistics that all models are wrong, but some models are useful. This is definitely a very useful one. So I should caveat everything I'm about to say by saying that I'm not saying we should throw away lambda CDM. I'm saying that we may have found some holes. Okay, so the way that we try to connect observations with theory is using detailed cosmological simulations. And hopefully this video plays. Okay, great. So here I'm showing a simulation from the illustrious collaboration. And on the left, you can see dark matter. On the right, you can see the gas particles. And in the dark matter box, you can see that there are these clumps over here of dark matter that collapse under gravity and merge to form increasingly more massive halos. And these halos are actually the sites of galaxy formation. On the right, you can see just how that happens. So on the right, you can see gas being accreted onto these dark matter halos, and that gas is being used to form stars. And so if we can take key observables like the masses of these galaxies and the numbers of these galaxies and these dark matter halos, we can then tie them back to what we are seeing in these simulations to try and understand any discrepancies that we see between theory and observation. And so the growth of these galaxies, as I mentioned, is closely linked to this hierarchical growth of the dark matter halos. Now, why do we think there's actually a problem between the galaxy that I showed, the extremely red galaxy, and lambda CDM? Again, with hierarchical growth, it takes time to actually form extremely massive systems. So if you have a galaxy like this that has the mass that's 3 times the mass of the Milky Way, forming at such a young age, how exactly did that come to be if things grow hierarchically in the universe? We don't really have a good explanation for that just yet. Some people have called this the impossibly early galaxy problem. And the basic idea is if you take the number of halos per volume, so the number of dark matter halos, and you plot them up as a function of the halo mass, and you look at what simulations predict versus what we get from observations, the observations predict that these halos, these galaxies are actually living in halos that are too massive to have formed by that hierarchical growth that we saw in the illustrious simulation. This is a illustrating the same thing but from an actual paper. So same here, number of galaxies per volume, and then the halo mass. And you can see here that as you go further and further in distance, this discrepancy actually gets worse. So again, what exactly is going on here? Another caveat, as a general rule of thumb, history has told us that whenever theory and observations disagree, it's usually best to believe the observational results, because the theories are best approximation of reality, but the observations are actually reality. And so with that guiding principle, and as an observer, usually the tendency is to go and get more observations, which will enable us to try to reduce that measurement uncertainty that we might have on, say, stellar masses or anything, any key observability that will help us understand what's going on in theory. The other thing that might be going on is that there are actually additional physics that we don't quite understand yet as it pertains to the growth of galaxies and how they evolve over time. And maybe that additional physics hasn't been included in our cosmological simulations. So for the rest of this talk, I'll be focusing on this aspect, getting more observations to reduce our measurement uncertainties. So how exactly do we find these monster galaxies? The problem is the universe and galaxies in the universe evolve over billions of years. And I'm probably not going to live that long. So we have to come up with innovative ways of actually capturing the evolution of these galaxies at various snapshots in time, in a time frame that makes sense. And so the way we do that is by taking snapshots of the same type of galaxy at different distances. So this is a series of Hubble images of a Milky Way-like galaxy and how it evolves over time. And so you can see that in these different snapshots, a number of different things are happening here. The galaxies look different in size, in color, in structure. And so taking these different snapshots give us an idea of how the physical properties of these kinds of galaxies are evolving as a function of time. And then we can take these physical properties and then try to tie them back again to theory to see what we should expect from them. The second strategy is to take snapshots of the same type of galaxy, but then at different wavelengths. And so the reason why we do that is here I'm showing the brightness of the galaxy that we saw before, XMM 2599, as a function of wavelength. And you can see here that it's actually really faint in the ultraviolet and in the optical, but it's brightest in the infrared. And so if we want to increase our chances of detecting these kinds of galaxies, we need to look into the infrared. Just to demonstrate again why we need to look in the infrared, this is the Hubble Ultra Deep Field image. The Hubble Deep Field image was taken in 1995. The Ultra Deep Field was taken in 2009, I believe. And here, this is a color composite optical image. And on the right, this is a color composite infrared image. And you can see on the right here that in the infrared, there's some galaxies that pop up here that don't really show up in the optical image. So I'm going to flip back and forth between the two so you can see that clearly. So we're going to go from optical back to infrared, and then optical back to infrared. And then I'll put my mouse on one of the galaxies that pops in and out. And then you can see that in the infrared, it shows up, in the optical, it doesn't. So these galaxies are really bright in the infrared, hence, that's where we need to look for them. Okay. Another thing we need to consider is the fact that these galaxies are really, really faint. And because I work with them, this has been the bane of my existence in grad school, and I'll explain why in a second. And so because they are faint, we use some of the world's largest telescopes to find these galaxies. And here I've shown the mirrors of some of the telescopes that have been used in the past and will be used to look for some of these galaxies. This is a human here for scale. So this is the Hubble Space Telescope. There have been numerous surveys with Hubble, the Canada, France, Hawaii Telescope, James Webb, Spitzer, now decommissioned, Gemini South, which is the telescope that I use currently, and the Twin Head telescopes, which I will be using in 2.5 weeks. And so, yeah, these telescopes, the reason why we use the largest telescopes is because the ratio of your signal to your noise scales directly as a diameter of your telescope. So if you want to increase that ratio, you need a bigger bucket. You need to use a larger collecting area. Like I said, the fact that these galaxies are faint have been the bane of my existence in grad school. This is an actual image, my data. You just take a picture of the sky, say a 15-second exposure in the infrared. This is what you get. It's not pretty at all. It looks nothing like the beautiful Hubble deep field images that I showed. You can barely see some of these bright stars that I showed earlier. Like, it's ugly. And that's because the sky is, again, the atmosphere, it's 10 magnitudes or 10,000 times brighter than these distant massive galaxies. So you have to go through, well, first off, you take hundreds of exposures, and then you go through this complex process of modeling the background, subtracting it, and then averaging these images to produce this beautiful image on the right over here that actually shows something more than the sky. So this is my handiwork. Yes, I'm showing off. You can take a look at it. Thank you. So the fourth strategy we use is not only to use the largest telescopes, but then to survey large areas of the sky. And the reason we do this is, if you plot, you can think of this as some measure of number. If you plot that against the stellar mass of the most massive galaxies in the universe, the Milky Way would sit somewhere here, Andromeda would sit here. You can see that there's this exponential drop-off by the time you get to galaxies like the massive one that we saw in the beginning. And so they are really, really rare. If we want to capture them, we have to look at really wide areas of the sky, just try to find them anywhere possible. So this image here shows some of the surveys that have been undertaken, with the moon shown for scale. With the Gemini South Telescope, I think we're surveying an area that is about 3 times that of Cosmos. And so hopefully we'll find some in the near future, fingers crossed. So what progress have we made so far based on the 4 strategies I just outlined? So this is a fly through the Hubble Ultra Deep Field. And I really like this video because it sort of gives you, I mean, when you take pictures of the sky, everything is 2-dimensional, but this is an attempt to sort of simulate that 3-dimensional effect you would get if you're actually in space. And they are flying through different galaxies, trying to highlight the different types. I thought it was so beautiful when I saw this. And some people have dubbed, not the Ultra Deep Field, but the original Hubble Deep Field image, which came out in 1995 or 1996. They've dubbed it the image that changed astronomy, because we ended up finding, before Hubble was launched, people said, oh, we're going to discover all these amazing things. And then there were some things that we chanced upon that we didn't know that we'll discover. And one of those things was these distant red galaxies. And so when I was digging through the literature to see what the history of, I guess, this subfield is and has been over time, I came across this paper. And it's a paper from 1996, it was published in Nature. They came across a galaxy like that, a really red, distant thing, like this one over here. That's the video is zooming into. And they realized that there were a number of competing cosmologies at the time, and one of those was the Einstein de Sitter model, which didn't incorporate the expansion, the accelerated expansion of the universe. And they realized that if you calculate the age of this galaxy based on absorption lines in its spectra, and you compare that to the age of the universe based on the Einstein de Sitter model, those 2 things were discrepant. You would get a galaxy that was older than the age of the universe. And so this was actually, the observation of these massive red galaxies was actually one of the things that debunked the Einstein de Sitter model at the time. And all the way from 1996 up till now, we've made quite a bit of progress. So here I've plotted all the massive red galaxies that we've discovered, their stellar mass, as a function of increasing distance from nearby universe up till now. Into the early universe. And you can see that as we go from local to the earliest times in the universe, we come to a region that we've largely not explored. These are some candidates that we think we might have, but really, this region here and extending even to further distances, this can only be accomplished by James Webb. So, James Webb will discover some of the first galaxies. This is a simulated infrared James Webb image when I saw this, I was extremely jealous because my image is nothing like this. It is a beautiful image, has so much detail, and I really can't wait to see what we're going to get out of this galaxy, out of this telescope, sorry. Some of the questions that we will answer, does star formation in the distant universe occur differently than nearby? And the reason why this is important is the physics of star formation determines exactly how many stars you are going to form, i.e. what your stellar mass is going to be, and how massive your galaxy is going to become. And so if there's something we don't understand about the physics of that, it's going to determine our results, and it's going to determine whether there is actually a discrepancy between observation and theory. Do population 3 stars exist? So these are stars that are theorized to be much more massive than stars that we have in the local universe. And if they exist, it might explain why some of these galaxies end up as massive as they do, even within the hierarchical merging and growth paradigm. How early does star formation occur? How early does it hurt? What are the typical quenching timescales in the early universe? What is the relationship between the most energetic events? So, for example, active galactic nuclei and when massive halos form, because those energetic events could quench star formation, and many, many more. I didn't have enough space to fit all the questions we could answer. But the point is, we're really excited about James Webb, and these are really key questions that we think James Webb will get the answer to. And if you want more information, there's this JWST Observer page on YouTube, actually. And if you go, all the Cycle 1 programs that have been scheduled for James Webb are actually listed there. And the actual astronomers behind those programs give, I think, 20-minute talks or so explaining their science, what James Webb is going to do with their science, yada, yada, yada. So check it out. And if you also go to this page, there are abstracts and other details of the very first surveys that we have with James Webb. So there's a whole ton of information. Like I said, yeah, no Pokemon jokes, but I hope you enjoyed the experience. So with that said, I will end here and I'll take your questions. Yes, please.
A couple slides ago, you had a quenchable timescale.
How long does it take for the galaxy to stop forming stars from the time that it began to get raid?
Does that require quenching?
Does that require quenching? Does what require quenching?
Start from galaxy formation, or what does quenching mean in astronomy?
Right, so quenching here means stopping star formation. So the point at which you are no longer forming any stars. Does that make sense?
Yeah.
Yeah. Yes.
It's kind of like, I think your first thing, like you said that it was forming like 1,000 stars per year for like 50% lifespan. But I'm just curious, like, what's the scale? Like, how many years does it mean this lifespan?
Can you repeat the last part of your question? How many years?
How long is this, like, 1,000? Like, how many years is this, like, 1,000 stars per year period? Or how many stars are these?
How many stars does it form? How long does it take to form the 1,000 solar masses per year? Is that what you're asking?
How long is the star formation like constant for? Like if it's 1,000 solar masses per year, how long does that sustain? How many years?
Oh, I see what you mean. So if you look at its star formation history, it's actually not, it's not constant at all. It peaks at 1,000 solar masses per year, and then it does that for about 150 million years, and then just rapidly, exponentially declines from there. So does that answer your question? So it's not a constant function at all. Yeah. Yes. Yeah, so she's asking how many galaxies like Ben Forest Galaxy do we know of? And the answer is, I think, in this plot. So if you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Like I said, they are rare. They're really rare. They're more numerous as you go to lower and lower redshifts, because they're not as faint and they're not as difficult to find. That's a complicated question in the sense that, so on the one hand, we don't actually know how many of these are there, right? We only know from current observations that there's that exponential cutoff in the mass function. And so it's possible that maybe a lot out there and we just haven't found them, or maybe they actually are rare. And so that's one of the things that having more data will help us do to actually answer that question of how many of that is actually there.
So you mentioned there was like the red galaxy found earlier. Okay, like, does every galaxy have a different color to it? Or is it just that one specifically has one color?
Yeah, I think every galaxy has a different color to it, depending on what physical processes are actually going on in the galaxy. So this one is weird because it's stopped forming stars, and so most of the stars in this galaxy are actually very old stars, which tend to be red in color, which is why it has this red. So if we had a more actively star-forming galaxy, you would probably not have this color. It would look maybe more bluish. Yeah.
So yeah, to answer Ryan's question about this star formation period takes hundreds of millions of years. If you're only allowed to take snapshots of the galaxy by taking photos of different galaxies, how do you know that that period was 150 million years? So by looking at one galaxy.
Yeah. That's a really, really good question. And I think the answer rests in, so when we are creating the star formation histories of these galaxies, we actually assume a certain functional form. And there are various forms that you can assume. You can assume that the star formation rises and declines exponentially. You can assume a constant star formation. You can assume all kinds of things. And once you assume that form, we go through, so we've calibrated a number of galaxy templates, but at lower redshift because we have better data there. So the combination of those templates plus the assumed functional form of your star formation history, plus some other modeling details that Justin would, he can't see him anymore. Yeah, Justin knows all about and can chat your head off about. And all those things combined are what gives you, are what allows us to use, to get a star formation rate and star formation history from just one galaxy. Yeah. So that's another reason why I think James Webb is going to be so important, because like I said, we've calibrated lots of these things at lower redshifts, so in the local universe. And so are these templates actually accurate in the higher redshift universe, or do we need to modify them based on the observations that James Webb will give us? Yeah.
So you talked about how the universe seems to be forming way more massive galaxies way earlier in time than the theories say that you should. As a theorist, like, no. Like I agree with your statement. We should trust the observations and tweak the theory. Mm-hmm. How should theorists be how, are there thoughts about what to tweak to make bigger galaxies earlier on in time? Like what are people thinking about tweaking?
Yes. So one of the major things that I think a lot of theorists who do this sort of modeling are discussing now are the AGN feedback in the simulations, because the strength of your AGN feedback determines exactly when the galaxy is quenched, which determines how massive it can get before it quenches, not including things like merging and whatnot. So that's one of the things that I wish I had that plot to show here, but if you actually take the different AGN feedback strengths in various simulations and then plot the number density of these massive quasar galaxies, you get one particular AGN strength that goes exactly through that line, and then the rest don't. And so that's probably the biggest thing to tweak. I know, yeah, there are other ones, but I think that all those other things, I think the AGN strength of the AGN feedback.
All our viewers.
What's AGN feedback? Okay, so active galactic nucleus in the center of your galaxy, it's spewing off, depending on which angle you're observing it from. You want to answer this question? This is your
Supermassive black hole in the center of a galaxy.
supermassive black hole. I just passed it on to you because I really like AG and Tora and things like that. Yeah, so supermassive black hole at the center of a galaxy. It's like accreting gas. That's those interactions between the AGN and the gas are causing all these energetic, again, explain feedback. I think of them as jets, I suppose. And then that energy coming up from the center of the black hole can heat up your gas. And for stars to form, you need the gas to be cool. So we're talking 50 Kelvin cool. So that's what I mean by AG and feedback.
Okay.
Yeah, thank you for all your questions. I'll be around if you have any more.
Thank you, Jacqueline. That was a very, very, very interesting talk. If anyone has more questions for Jacqueline, she's right there, I guess. Okay, we are going to go over the answers for trivia now. And the winner gets free stuff. Talk to Sylvie later. Okay. So, question 1. What astronomical phenomena did Benjamin Banneker write about in his almanac?
C.
I think you guys just saw the answer, so. It is indeed C. Solar and lunar eclipses. Okay. Who is the author of the book Hidden Figures? Anyone? You are correct. Okay, question 3. In what year did Harvey Washington Banks become the first Black person to earn a PhD in astronomy?
A.
It is B, 1961. Question 4. Who was the first African American in space? I'm hearing A, I'm hearing B, C, D, all the above. E, okay. It is in fact not E. It is Guyon Bluford. Okay, oh, well, there you go. University of Maryland.
Okay, Barbara Williams, University of Maryland, 1981. She became the first Black woman to earn a PhD in astronomy. Oh.
D.
Hey, how many PhDs have been given to Black women in physics and astronomy in the US? D, 187. There's been like thousands of PhDs. Okay, question 7. Gregory Robinson is the program director for which space telescope? JWST. Woo. Question 8. Who is the most published Black astronomer? Gabro Barsi. Question 9. Whose memoir is titled Time Traveler, a scientist's personal mission to make time travel a reality?
Gabro Barsi.
Good guess. Ronald Mallet. Question 10. Who has had a sack in the Super Bowl and also has been to space? I don't know what a sack in the Super Bowl is. Oh, okay. Well,
When you tackle the quarterback.
okay. It is C, Michael Strahan.
With your
Strahan. Okay. This is funny. Yes, and our winner tonight is, drumroll please,
Shelby.
You can come talk to me and then we'll talk about prizes and options.
Yeah, okay, so last thing we're gonna do, this is basically the conclusion of AOT for this month. We're gonna go over announcements one more time. So I hope you had fun tonight. If you did, please like and subscribe to us on YouTube. We also sometimes broadcast solely on YouTube, but hopefully we'll get to do it in person as much as possible. And then follow us on all of our social media accounts, AoT BCS, Twitter, Instagram, Facebook. happens in other cities and whatnot. And please tip your bartender for your Stafford drinks. Then put Stafford tip in the description, please. And if you would like to donate to us, you can send us money on Venmo or Cash App at AoT BCS. And if you donate $15, you could get a t-shirt or a mug, your choice. And if you donate $2, you get a sticker.
Stickers are also just free.
Oh, okay, so they're just free. But also you'll get a sticker if you donate $2. Your choice. We have new mugs that Sylvie made. So yeah, $15 donation, you get a free mug. And our next event is March 23rd, 2021. It's always the fourth Wednesday. Oh, no, 2022. March 23rd, 2022. Yeah, we're all gonna time travel, meet here, see you next year. See you last year. Okay. Yeah. Okay. And if you have any more questions for us, please talk to local astronomers. We have glow sticks on. I don't, but I have purple hair. I'm pretty easy to spot. And I think that's everything. See you next month.
I